Hello, Augies Worldwide. I'm Dave Kassler, amateur radio call sign KE0OG, here with another episode of the Commentariat. And this is for 17 May. And what we do in this is we'll just go through some comments. You can tune in as long as you want and see what's interesting. Leave your own comments, of course. The video that just went up, I think yesterday, was a set of charts made by an Augie that he sent to me for how he used a nano VNA to solve a real-world problem that he had with getting a transmission line about that far from a little circuit board antenna, GPS antenna, over to the receiver itself. When he measured the impedance of it, it was badly off, so he used the nano VNA and the Smith chart to determine what he had to add to that in the way of reactance to make it work. And it really was a very interesting set of charts. I hope I did them justice because Smith chart is an area I don't excel at and definitely don't excel at, rather the opposite. So this was kind of a chance to see what a Smith chart can do for you. Smith charts are on antenna analyzers, and it's very easy to think of them as something to analyze antennas, when in fact they are designed to analyze transmission lines. So anyway, very interesting to look at. So let's take a look at the comments, starting with Bob Mellor. Is that right? Mellor. Very interesting, Dave. Thank you, 73 Bob. This is regarding to the real-world charts there. Delta X-ray 444. I will admit, regardless of any explanation I've watched, this nano baffles me. SWR and feed line readings are readings, but for resolving or investigating any other issues, I'm lost. Well, Delta X-ray DX. I agree. But it's interesting to learn about. I'm thinking I'm going to have to learn more about these Smith charts. They're turning up on all new antenna analyzers. So people are going to want to use them. They're going to look at them. They're going to wonder what they're about and so on. So I need to figure that out so I can talk to people about that. I do use my nano VNA for SWR. I'm very good at getting right to that particular point. I even did a video on how to use it for SWR. Now, the nano VNA does a lot more things than just measure SWR. And that's true of most of the new antenna analyzers. They can also analyze networks and tell you what the phase change will be and all of that sort of thing. So anyway, Christopher Andrews, Victor Kilo for Golf Delta Lima in Australia, says the nano VNA definitely punches above its weight. W2AEW, who is sort of the most technical of the ham radio YouTubers, has a video on tuning a diplexer. Here is the truth serum. I want to build an RLC circuit with all variable components to add to my antenna lab. I've already sourced a variable plate capacitor, a log potentiometer, and we'll hunt down some variable inductors. It's like building a wah pedal circuit for, let's see, a wah pedal circuit for RF. I will run some spreadsheets to determine the ideal tuning ranges. Yeah, absolutely, you can do that and play with it. Now, you note that a capacitor across a transmission line is kind of the equivalent electrically of a inductance in series with it. They kind of swap. The one is the reciprocal of the other, and they can be very interesting to play with. Motham51 says, nice Dave, fun stuff. Glenn Martin from Far West Missouri says, thank you, Dave. Amazing how tiny things are now. Boy, that's true. And I just did a video with the little tiny spectrum analyzer, which is not much bigger, and show how it can very quickly do the measurements that take a while longer on my big spectrum analyzer, I usually put radios, new radios from China, those are the ones I get, and put them on the spectrum analyzer so we can see what kind of harmonics we're dealing with. And I took a radio that I knew what the answer was and used it with that little device, and it showed all the same harmonics, so it was really now. Bob Carnaroli says, I had no idea how to make changes to the reactance on the Smith chart. Yeah, it's kind of cool how you can do it. I had to take his word for it because I don't know. But you have these lines of constant inductance, and you can follow them along until you hit the line of constant capacitance, till you can create a path to the center. The center is where everything is one-to-one. One thing they don't talk a lot about with Smith charts is you have to normalize everything. The center is 1, not 50. So you have to multiply by 50 or divide by 50 to get the things that you are looking for. Okay, and some Smith charts, have the origin here with the big circles out. Well, a full Smith chart has the capacitance circles coming this way. So it's quite interesting how it was done. Okay, Mark G. Mine is used for antenna check, tune, and coaxial cable verification. I can see it on the length of my coax cable and if any open short within the distance of before my antenna. This, by the way, is a great way for looking for faults in a coax line because it'll either be open or shorted, and thus you'll get all the power reflected. And if you look at the thing for distance to fault, it will give you that distance out there. And it's really quite interesting. I can do a cable impedance check too if needed. For me, it's a must to have in RF. Yeah, a lot of people really enjoy it. And, I think as these things become more capable, we've got resistance. We've always been able to measure resistance, but recently fairly reliable capacitance and inductance meters too. Okay, and the antenna tuner became popular after the first all-transistor radios came from Japan, because then you had to have a good feed line and transmission line. The tuning circuit on the output of a tube amp is what's called a pi filter, or pi network. And that actually acts as an antenna tuner. So you can have fairly wide mismatches between your transmission line and antenna and so on. The pi network will take care of it. Now that's the transistor amps that came out did not include a pi network. You had to feed to a 50 ohm impedance and you had to make sure it was close. So people started coming up with external antenna tuners and antenna analyzers so you could tell where your antenna was. So as we get more capable test equipment at a price range we can afford, we naturally become more curious to understand what we read on the meters. And it's amazing what we can read on those meters and learn a lot more. Now, several years now, I acquired a real oscilloscope. Now you can get a little oscilloscope that'll read out on your phone or your iPad or your computer. They're not as exotic as a real one, but if you're just looking for signal shape or trying to understand a phase difference or something like that, they can be pretty capable. Let's see, Nano, that's the game changer. Yeah, okay, very much. Cost was a big problem for a network analyzer. They run over $10,000 for a lab grade instrument, sometimes significantly more, and they can get one for $50. ASDF Says, you're the man, Dave, 6 months ago. Nano VNA too complicated, don't use it. I know. I said that. I had a little ceremony where I ate some crow. I had to be taught how to use it. Tom Ferrix on the Front Range talked to me for quite a while, but I really had to dig in and study. And then I had to understand what order to do things and what I was doing with them. The thing that helped me do that was to get a complete printout of the menu structure and then run through and understand the vocabulary. That's why I started my video about how to use nano VNAs with a vocabulary chart, because the words appear to be in English, but they're not. They mean things other than what we would normally think they mean. So if you think like the people who wrote that, you can use it very easily and very simply. Okay, George Dom, again, we're still using the nano VNA to solve real-world problems. Somehow this explanation of Smith charts actually clicked with me, whereas the explanation in the extra handbook just kind of bounced off. I think the real-world context helps a lot, at least for how my brain works. I have a nano VNA and have actually used it to tune some things, but I'm still suspicious of its accuracy. Without having a 14K VNA to compare to, what could I do to validate the results, and particularly for things more complex than a simple SWR reading? In the presentation, he says at 1310 here, where I did directly answer the question of how accurate they are, and that is within a few % of the real expensive one. Now, you can calibrate it. A lot of them do come with little calibration devices. One is a short, one is an open, and one is 50 ohms. And if you follow the procedure, 50 ohms should absorb everything. The open and closed should reflect everything. And by using just those three, you can calibrate the meter pretty well. So I think, George, that actually does sort of answer the question. Make sure you get a nano VNA that has the calibration devices. Mine does. Mine came from Walmart. I did not find out till recently that there's a place in the United States where you're supposed to get these things. Okay, the nano VNA comes in a package just like this, and it's one of those packages that lasts forever. And this is where they come from. R&L Electronics. And the URL is given there. R, the word and then L. Or Randall. RANDL.com. Okay. If it's out of stock, go ahead and order it, and they'll get it to you pretty quickly when they get more in. They're selling them pretty much as fast as they can get them. But this setup that has all the things in it that you need, let's just take a look and see if mine has the calibrators. This is the spectrum analyzer, so it doesn't. But the nano VNA does. A nano VNA is designed to measure some things, and if it knows the errors on those three key pieces of equipment, you can be pretty sure it is correct. Now, one thing I will point out on the nano VNA, it does not have an automatic memory. You have to save the settings, the calibration settings, and then before you use it the next time, you have to retrieve those settings from memory. Okay, they're not kept in a non-volatile place that it can normally get to. Okay. Now, this is a video on Ham radio magazines then and now. This is number 740. This is from Thor Music. Another great video, Dave. I was a member of ARRL for many years, but let my membership lapse a couple years ago. I like the idea of the league, but feel that as an organization, they've done an increasingly jolly job of... I'm really not sure that's true. If the telecoms wanted to commandeer the ham bands, the feds would no doubt thanklessly relinquish them, probably without batting an eye. I know there's a big thing there as hams. What we need is an organization with the stomach to fight the political battles with gumption, not just with lip service. Okay, let me caution you, however. If you're driving a little compact car and you come up against a Sherman tank, who gives the right of way? The answer, of course, is you do, because that Sherman tank will just roll right over you. You can yell and you can squawk and you can do all you want, but the Sherman tank is going to roll right over you. And it's the same thing. If there is a stretch of spectrum that sees rather light amateur use, and they can put that piece of spectrum to better use by millions of people who will use it for 4G, 5G, 6G, whatever, what do you think would be in the best interests of the government of the United States? And the answer to that, of course, is they're going to go with the telecom companies. Now, the FCC has proven pretty protective of our HF frequencies and occasionally throws a SOP our way, like the 60-meter band. And there is some hope that they'll allow technicians onto HF if they'll just ever get around to responding to the league's request. But those microwave bands, they were given to the hams because nobody wanted them. Okay. Also, the FCC realizes that if they allow the hams to use things, they're going to invent stuff for those bands that will be useful to other people. And we have proven over and over again that we can do that sort of thing. So, which is better from a governmental point of view? Using spectrum to serve millions upon millions of people, or spectrum to serve the 500 or so hams who do microwave? Well, I think the answer is we're going to have to be happy with what we are given. Now, we still do have ham bands. There's going to be some pushing around of the microwave and so on. Now, let's take for an example. Airlines are very influential. Airline safety is a watchword. Okay? Airline safety is a watchword. G5 interferes with aircraft radio altimeters. They use radio altimeters on landing to designate how far above the ground they are, and it's an extremely important piece of information, because if you've ever sat in the captain's seat in a great big airplane, you know how far it is to the ground. And you've got to come in and land, and you've got to put that back set of landing gear right on the ground at just a certain point on the runway. Now, a lot of that can be done manually, but sometimes pilots have to fly the planes themselves, and they can't do it automatically. So the FCC has basically told the airlines, we're sorry, that's wonderful, so bad to hear that, get yourself some new equipment. And it's going to cost the airlines $1 billion or so to do that. But rather than just a few airlines using it, what the problem is not 5G per se. It's that there is a band for this, it's sort of a belly radar that checks, and it starts working at about 25 feet and gets all the way down to 0. Now, the thing is that if the equipment on board the aircraft were built properly, they would not have receivers with very wide input filters. They would filter it just for the little part that they need. But no one else was using the band spectrum, so they built them so they were wide. This is a problem with GPS receivers, too. And if GPS receivers actually only received what they were supposed to receive, we wouldn't have these impact problems. But that's kind of the history of what's going on here. We can have the ARR yell and scream all at once. But you don't have 800,000 hams who want the microwave bands. You've got probably 800 to 1,000 who actually use them. Okay, it's a small, tight-knit community of people who use these bands on occasion, usually for contests or prearranged record setting. Now compare that with the 8 million people in a given area, in a metro area, who want to use 5G or whatever's coming up. We've got to get some sense of we're the little gnat that's going to get run over by the Sherman tank. It's just going to happen. So we should be grateful and remember that we have no more claim on these frequencies than is laid out in the 5 purposes for ham radio. The beginning of Part 97 lists the purposes of ham radio, and everything we do is going to fit one of those. Otherwise, the FCC is not congressionally mandated to provide us with the frequencies to do that. Okay, it's got to fit those purposes. They may sound like blueprint or hogwash or, whatever. They're actually extremely important. And we have to be able to point back to those and say, if you take this band away from us, we are not able to do this and such. And it's important to the purpose of amateur radio, which is important to the American people. So I think that is where we need to understand where we are. And the League understands that extremely well. Okay. This is the ARRL NFED half wave, which I commented on in, I think, the May QST. And I put the thing up, and we did some tests with it. We put it up, tested it, it works fine. And then, based on a letter from Nagy, I extended it to 180 meters, and it works. And then, based on information from that same Augie, I made a little tiny mod with a little tiny capacitor at the center. And we got the thing, the 80-meter part, to move up substantially while not affecting the 40 through 10. And then, at somebody else's request, I checked how it worked on the work bands. It doesn't work at all on 60. But on 30, 17, and 12 meters, it does work. The antenna does work. It's about 2-to-1 SWR, but you can tune that out with the tuner in your rig. So let's see. Curious how it looks 160. I never used it. I used the infamous mystery antenna for the bands except 17 and 15. I'm shocked that my LDG 600 PRO Pro 2 tuner can find a match on 160. I got surprisingly good results running 100 watt on 160. Well, very good. That's the spirit of ham radio. We try things. That's a quarter wave on 160. So I guess with a good counterpoise, that should work. I'll have to check the thing out. I've got it here and see how well it does on 160. Let's see, Mark Doyle, why 50 ohms? I thought the heaviside layer, or lair, was from Cats. Cats was a Broadway musical decades ago now. I guess it was a movie too. But the heaviside layer, the layer is where the cats are. The heaviside layer, which is the ionospheric layer, before it was fully understood and broken into the different parts. Oliver Heaviside postulated that there must be such a layer. There was another guy called Kennelly who kind of did the same thing about the same time. Sometimes it's just called the Heaviside layer because Oliver Heaviside was a wacko genius. Okay, he invented operational calculus. He solved a lot of problems that other people were having trouble solving. He was a crazy guy. He came pretty close to anticipating relativity. At least some of his papers seem to be headed in that direction. When he died, he fell off a ladder. Idiot, the age he was, going up a ladder. Although I shouldn't say much. I burned myself pretty badly going up a ladder. When was it? Last July. Anyway, he fell off the ladder. He died from injuries suffered in that, the after effects of that. He was a brilliant man, although like most really brilliant people, a little weird. I've got a book on him that explores the weirdness, as well as it's actually written by or published by IEEE, so it's not afraid of technical stuff. And it goes on in there to describe what it was he was trying to do with the operational calculus. You know, so many mass market documentaries, like, say, of Einstein, talk about his love life, being a Jew in Nazi Germany, coming to the U.S., getting awards, all of this kind of thing like that. And not one of them begins to turn the page on even special relativity. I mean, what he is famous for is not his haircut, but his theory of general relativity. And to understand the man, you've got to take a few minutes and try to understand general relativity. It is, to this day, 100 years after its formula, more than 100 years after its formulation, the best model of cosmology that we have. It's just the best. It keeps being proven accurate over and over again. Einstein expressed his equations in tensor format. And I have looked up what tensor means. It's sort of like a matrix, only different. It's like a matrix of operations. And no, I don't understand it. I mean, I understand kind of the bit about, the equations and the fact that time is one of the four coordinates of the universe, and so on and so forth, time dilation, and all that sort of stuff. Anyway, not much. You don't need to know that to get on the air. You don't even need to know Maxwell's equations to get on the air. I should point out, Maxwell's equations today are listed as four equations. Four equations. However, Maxwell didn't make four equations. He made 21. And they involved quaternions. Heaviside hated quaternions. And so with his operational calculus, he re-expressed the 21 equations as four. And so these are really Heaviside's equations, but they are merely an expression of Maxwell's thinking. And we use the Heaviside form of Maxwell's equations today. And they're really interesting because we talk about magnetism and electricity being kind of the opposites of the same thing. They're not really. One is the derivative of the other. And it's really quite fascinating to take a look at those. By the way, in my math textbooks, when we got to the part where we were exploring that math, curl and divergence and all of those things like that, we were doing it in a more general form with multiple dimensions rather than just 3. And there was a footnote, literally a footnote in there that said, in 3-dimensional space, a special representation of these theorems would be these 4 equations, which are often called Maxwell's equations. And people tend to use them, but they're not important to us because we're mathematicians. It's basically what the footnote said. It's kind of weird. Okay, N0VTY. Added a couple turns to the tuning coil for my end-fed half-wave and brought down the upper bands above 20 meters. A little bit of time with an end-fed half-wave will bring all the bands well within a 2-to-1 SWR 80 to 10 and less. But move the antenna a little and all the tuning changes. Yeah, what you are tuning, you're not just tuning the antenna, you're tuning the antenna in its environment. Okay, remembering that the first rule of antennas is everything affects everything. So, yes, that is true. Although across the entire 80-meter band, I'm not so sure. But you can certainly get a large part of it, like a third, something like that. Cletus Neighbor says, I just put up an end-fed dipole, flat horizontal orientation, going from house to the east. What will my radiation pattern look like? Better north and south? Well, that depends on where you are and what you want. By the time you got flat horizontal orientation, understand that the pattern will change with each band. If you go into the antenna modeling software and look at the way the pattern is, you've got one height. It will act one way on 80 meters, differently on 40. By the time you get to 20, it's starting to look more like a regular dipole, except because it's so long, you get these weird patterns on there and so on. You get some very weird patterns with these antennas. Now the question is, which is best, east, west, north, south? And I would venture to say the best orientation of a dipole antenna is where you can fit it. Okay? Where you can fit it. Now, if you have options, you can make it so that what you most want to talk to, say you want to do DX to Europe, put it so that the Great Circle route from Europe is at an angle for you. This is an example of an azimuthal map centered on my location. Okay. And then I kind of zoomed in for the U.S. so I could see where the states are. If you go to ns6t.net, that's November Sierra 6 Tango, period. November Echo Tango. If you will go to that, you can make one centered on your location. And it does make a difference. The League offers such a map, but it's centered on the center of the U.S., so it's only... if you notice on this thing, Australia is due west from me. Okay, so that's where I would point the antenna, is due west. If I wanted to get to Europe, which is up there, I've got to go pretty much over the pole. Okay, so you too can make a map like this. I should do a video about that. It's a nice little map. That will help you orient it a bit, but again, remember that obstructions, reflections, and so on can make it go a different way. Plus, dipoles that are near to ground are, I won't say they're omnidirectional, but the difference between the best and the worst direction is often less than an S unit. Okay, so I mean, I'm talking about real dipoles above real ground. I don't know why, and I will say this to my dying day, I guess, why manufacturers insist on showing antenna patterns that are correct in free space with no ground reflections affecting the antenna. Because I do not know anyone who has an antenna in free space. Even on the space station, you put a 2-meter antenna on that thing, you're working against the entire space station. And that will affect the pattern dramatically. Okay? Now, if you put an antenna up high enough on a tower, like a 100-foot tower, won't that be like in free space? No, not at all. Model it. You will get, with that up at 100 feet, you will get very weird vertical patterns, some with deep nulls in between the vertical patterns. This is why rich DXers might have a tall tower with like 2 or 3 Yankees. And they'll pick the Yagi that best gets them to their destination, which may not be the top one. Because when you put an antenna up high, you start to get a lobing in the vertical pattern if you go above a half wavelength. That's why I say a half wavelength is often the best height for an antenna, because you have a single lobe and you're putting all your power in it. Now you can lower that lobe slightly if you raise it slightly, but you're going to slightly lose a little power. So depends on what you want. Okay, Stephen Coote, about how to read cross needle meters. Thank you. I just bought my first crossed needle meter, and now I know how to read it. Best wishes from New Zealand. Well, best wishes to you too. Now this is on the amazing performance of the ARRL antenna on the work bands. Thank you, Dave, from N0QFT, Glen Martin in the Far West Missouri area. Michael T. How close can the bonding wire coming off the antenna mast be to the coax running from the antenna mast as well? Well, actually doesn't matter very much. In theory, assuming you're going to take your coax and bring it over to the ground rod that's right next to your station, okay, where you have a lightning arrestor, and you're going to connect it into the lightning arrestor. Then you're going to come out of the lightning arrestor and go into the house. Okay, so the NFET antenna can use the shield, the outside of the shield, from there to the ground point as a counterpoise. Okay. Now, if you use an additional counterpoise and you find it works for you, experiment with where to put it, because it's going to be entirely installation dependent. Now, my test coax that I use for all the different antennas that I test is a 50-foot piece of RG213, and it ends at a lightning arrestor, and then there's a length coax into town to the A position on the switch over here. So I use that when I'm testing antennas. Right now connected to that is the ARRL antenna. And it works beautifully, and I don't need to put an additional counterpoise on the antenna. Now, the counterpoise with the antenna, if it just won't tune, try a counterpoise. Try something 10 foot. Dangle it. Throw it around. Make it 20 feet. Dangle it. Throw it around. Whatever. Until you get something that works. The difference between a counterpoise and a ground is resistive. It dissipates heat. A counterpoise is reactive. It's more like a capacitor. It stores current and gives it back. Okay. And you lay it at, this is one of the reasons that I recommend insulated wires for radials and not grounding them at the end, is so that you can get that, you've got a signal push up here and then the signal goes out the radials, gets pushed back up here. And the radial length doesn't matter much. The number of radials once you get past 16 or 20 doesn't matter much. But I have tried bare radials sort of, just under the surface of the ground, which people say works fine. Actually, that's a great grounding system. It's not a great counterpoise. And so the vertical needs those radials, not a grounding system. Now, it's the most permanently installed of all the antennas I have, is the Step IR, Big IR, and it has gazillions of radials. I put a lot of radials on it. And it's got a ground rod. And then it comes over here and it's grounded again. And it works really well. My next most permanent antenna installation is an MFJ hex beam that sits right out here in the yard. And it's on top of a 20-foot piece of Schedule 40, 20-foot, a full stick of the pipe. I have one strong pipe. Well, I'll tell you, that's a whole lot stronger than the chain link fence top rail. I got to tell you. And I really worked out and measured exactly where the guys would go. The guys sit at exactly 45 degrees. I've got actually 3-foot stakes pounded into the ground with maybe this much out, so you can tie the guy rope to it. And I say it's the next most stable. The thing actually sits on a base built for me by a friend where there's a bolt through, 2 bolts through the mast so that it won't twist as the antenna rotator up there does its thing. Because if you just use an ordinary mast, they'll work against each other and who knows where it'll be pointed. So anyway, that's just a little footnote on my own. So I think the answer is the outside of the coax is probably acting as a counterpoise too. So they will interact with each other. This is from Dave AC3HT, who added $5 to his comment. That $5 goes into the channel funds. Thank you very much. Dave, thanks for the video. My unfed half-wave works great on the work bands. The internal tuner in the radio easily touches up the SWR in the mentioned work. Okay, and Caden Christensen says, mine does the same for 12 and 17. 30 is a bit above what an internal tuner can do, but easy for even a basic external. Yes, very good. Okay, and John Hood says, hey Dave, I think you've mentioned that you had another wire antenna up at the reference station as the reference station antenna. It's not up right now. I took it down to put this other one up. If they're both roughly the same height and orientation, it'd be fun to have an A/B test, the reference against the unfed halfway. See if any difference. Yeah, you can certainly do A/B tests, and a lot of people do them. That, by the way, is how I found out how lousy the so-called Skyloop was. It's a horizontal 80-meter full wavelength loop. And I only had it up about 20 feet because that's about all I can manage here. Kent Klein has just emailed or mailed to me some instructions for how to do a good job of making a 30-foot stiff mast that I can then guy at a little bit higher altitude. And I'm going to look for those according to the email I got from the post office where they give you a list of what came in. It's here today. I'm going, however, into Montrose. Finally going to see the guy about my eye, the one that doesn't see worth a darn anymore. And see what's going on with that. Okay, so okay. Yeah, it'd be good to do the AB. I was saying with that loop, I had very carefully restored the HF9V, and I put it up with proper radials, and my wife and I tuned the thing. She sat in the shack with the SWR meter, and I was outside, and we were on the phone to each other, and we would talk and we got that thing tuned beautifully. And that thing performed so much better than the loop. And I found that out by doing A/B tests. Does this sound better or does this sound better kind of thing? That I actually took down the loop, cut it into more radials for the HF9V. Now the HF9V was up for a couple more years. And then it got to the point where if the wind was blowing the least little bit, and it rocked that antenna, it would make connection, lose connection, make connection, lose connection. And it was not a good thing. So I finally took it down and replaced it with the big IR. Okay. Amazing performance. Dave, how high off the ground? None of the instructions seem to cover that. Okay. How high off the ground? This is the conundrum of multiband antennas. I posit that the optimum height for a dipole is a half wave. And the reason for that is because you get the lobe down the lowest to the horizon, and it doesn't start to sprout more lobes. That's the point. You go anywhere beyond it and it starts to sprout a second lobe. And you go up to one wavelength and you've got two lobes with a deep, deep null in between. Okay. So the problem is that half wavelength height is different for each band. So if you have the thing at 33 feet, that is the optimum height for a 20-meter antenna. But it's certainly far from optimum for 40 meter. It's only half a wavelength high. And for 80 meters, it's only a quarter of a wavelength high. And the thing is then that on the 80 meter, most of the radiation will go up. In fact, the center of the beam is vertical, overhead, straight up. Now that's great when you're doing NVIS. And yes, you can use the antenna for NVIS. Now people talk about NVIS near vertical. It's nowhere near vertical. 45 degrees is nowhere near vertical, but it can go from vertical and out a bit, and you end up getting an area around you maybe 500 miles wide. Okay, now if you're in California, that's plenty of people to talk to on 80. Okay, if you want to do DX on 80, not the right antenna. Although that doesn't mean it won't occur. But get it as, okay, I know this is real technical. Get it as high as you can. Okay. As high as I can get it is 20 feet, which means near vertical on 80 meters and so on, even though I get a nice SWR. That's great. It's taking all the power and it's shooting it straight up. When you get out to the other bands, it's better. Okay. I know the my antennas, the company, my antennas, suggests even that their end-fed half-wave 80 through 10 antenna be down a little lower at the ends, like 7 or 8 feet, so you can walk under it. You won't get guillotined by it. And goes up to like 20 feet in the middle. That's a inverted V. And that's the way I put mine up, and I was amazed how well it worked. It worked really well. But it's high off the ground as you can get it. I mean, within reason. Okay. Terrence Barfield is about a live stream. My question, Dave, please tell me, what is the RF mode? What is the RF mode? There's a MDE. Not sure what that means. What is the RF mode? Up of coming out of transmitter, please, Dave. Terrence from London. Terrence, you might try that one again. Oh, here we go. He tried it again. Dave, Terrence from London, please tell me, what is the RF made up of coming out of the transmitter? It's an AC signal. It's called RF because the frequency of the AC signal is at radio frequencies. And that's what's inside that coax. All of the energy and information associated with that radio signal is inside the coax. That's the beauty of coax. Don't use RG8, RG58. Use RG59 if you must. I'd rather you go with RG8X because it has 100% shielding. Better yet, the LMR series, which has double 100% shielding, is really, really good shielding. And that keeps absolutely everything about that wave in there. Now, you are correct in asking what is it? It's an electric field, electromagnetic field, that is contained entirely within the coax. In terms of electron flow, you'll find that the electrons travel on the inside of the shield and on the outside of the center conductor. That's why in LMR coax, the center conductor is made of aluminum coated in copper, because most of the RF current electrons will flow in the copper. Now, if you want to get a little wild about this, remember that circuit theory, which is the kind of thing we talk about normally with Ohm's law. We talk about resistors, capacitors, inductors, and crystals and tubes and transistors and all that sort of stuff. Circuit theory is a subset, a rather small subset, of electromagnetic field theory. Now, you cannot explain transmission lines or antennas in terms of circuit theory. You have to look at the actual electromagnetic field theory, in other words, Maxwell's equations. And what you will discover is inside that coax is an electromagnetic field which flows at the speed of light in that material. Remember, light slows down in dielectrics and conductors and so on and so forth. The so-called velocity factor, meaning the fraction of the speed of light of flow, like for wire, open wire, is 0.95. Light slows down by 5%, or it travels 95% as fast as it would in a vacuum or in air. Speed of light in air is very little different from the speed of light in a vacuum, almost the same. So what you have to think of is that there's something going on in the coax more than just wires and electrons flow. Electron migration, as the current flows at the speed of light in that medium. The electrons themselves will move less than an inch an hour. Not very fast. But they bump each other and push each other, and the push goes down the conductor at the speed of light in that material. So I hope that helps answer that question a little bit. It is RF. You can measure voltages and current and frequency and phase angles, and you can measure the waves going and measure the waves returning and stuff like that. There's a lot that goes on in a transmission line. Circuit theory strictly does not apply. Circuit theory, strictly speaking, does not apply in antennas either. You have to have the conductor. This is the dichotomy. You have to have the right conductor. You can't just put up a piece of string and expect it to guide and manipulate an electromagnetic field. It has to be a conductor. Okay? And what is between the outer conductor and the inner conductor on coax, or what appears around an open wire line. In an open wire line, the field is around and between those things and goes out around it, and that's why you can't lay open wire line flat. You've got to keep it up in the air for it to work right. Otherwise, it starts to get lossy. Whereas a coaxial cable, everything's inside the coax. I've said enough. I'm just repeating myself here. Okay. So that's what the RF is made of. Okay, Wild Bill 1 says, I use an end-fed half wave, and those SWR measurements are going to vary with height above ground and orientation. Absolutely. Terrence Barfield says, evening, Dave. Please tell me what is RF out of transmitter made of? Okay. I think that was trying again the same question. Jose, Joe B. Dave, have been working with ham bands. Oh, this is a real long one. To cover, I extended it as you subscribed with another about 65 feet of wire, except for the top of the 80-meter band, which was the subject of my question addressed in the May 2023 QST, all or below 3-to-1, and tune. Okay, for 60, you're going to have to do something, change the thing, in my opinion. The NFED and the NVS isn't inexpensive. Yes, it is. By the way, Saturday's crossband test had a lot of good luck. Okay, great. Terrence Barfield, in all your talks, you have never mentioned about formula about what height at all frequencies should antennas be placed. In fact, I have. I've got videos on the optimum height for antennas for dipole, and that's where I made the assertion that the ideal height, if you can, is a half wave for horizontal antenna, because then you will get a nice single lobe. It's as low as you can get it without it starting to form a second lobe. I should maybe make that a little bit more specific. I can do that now. Okay, let's do that. Terrence, and I talked about, okay, it keeps coming again and again. Please tell Terrence, what is the RF coming out? I want to know what actually is makeup of RF of our transmitters. Again, it's an electromagnetic field. The transmitter is designed primarily based on circuit theory. Once it leaves the transmitter, it goes into a transmission line where impedance becomes important and so on, going up to the antenna. What you have coming out, you have volts and amps, absolutely. You have a frequency, but it's an electromagnetic field that's being conducted down the transmission line and radiated by the antenna. Another way of looking at an antenna is that it is an impedance matching transformer between the 50 ohms of the transmission line or the feed point of the antenna, whatever it is, and the impedance of free space, which is 377 ohms. Okay, so that's the farthest out description I can give you of what's going on. By the way, it keeps coming out. The same question over and over again. Prepcom claims that their decoders are capable of decoding in a noisy environment. Is that true? I don't know. I've never seen one. This machine decoding of Morse code is an unsolved problem. I have to look at Prepcom and see what claims they make. I'd like to see it, and I'd like to see it with hand-sent Morse. The G3 TPW cobweb antenna uses speaker wire and passes one wire through the feed line box, and the other wire begins and ends at the box where both ends get tied to the coax connector. The outer ends are tied together like a folded dipole. Apparently this gets up to 7 dBi gain and is omnidirectional. It's about what you're going to get with the regular one. They are omnidirectional. I don't know about that. The G3 means Great Britain. I don't know. I haven't heard about that kind of antenna. Stealth Man of the Woods. Okay, here is something in French. Oops, that's not going to do it. Copy. We'll go up here to translate. Okay, we're going to put it here. This is what we put, what he put in. This is what came out. Good evening. Is the programming cable compatible with Windows 11 on the Baofeng? The answer to that is, this is the review of the Quancheng Nuvi K5, which I just used the other day. It does not come with a programming cable. However, the standard, like the one sold by PowerWorks called the red cable, does work. And I've used that a lot. Does your ALS 500M work on 10 meters? I do not believe that mod has been put in. Okay, you don't really need 500 watts on 10 meters. If it works at all on 10 meters, 100 watts is plenty. Donald Smith, do you need to twist together for it to work? Many options. It is a pain to get them twisted together evenly. It is easier to just wind them around the core. Yes and no. The care and feeding of toroids and the making of transformers and so on, oh my goodness, we're over time, is a dark art. And sometimes you need to twist it very tightly, sometimes just loose coupling. And I don't know enough about it to talk about it. I have tried looking up books on these things, but, you know, we move there, we cross from amateur extra into full engineering territory. And most ham stuff, they say just do it this way. There isn't a lot of guidance for those sort of things that I have seen. So I'm sorry I can't answer the question. Glenn Martin says, Dave, I have found some strange things on the internet. Sometimes I experiment and find it works. Many times it does not. That's for folded dipoles. You can, yeah, there are lots of different things you can do. Okay, yeah, when you make comments, please make sure I can understand it from the context. Some of these videos were made years ago, so it's a little hard to remember just what to do. So we are going to stop there, and I'm going to stop that recording right there. I'll stick it in the right place in a moment and say to you, thank you so very much for being part of this channel and helping this channel succeed. I think we kind of enjoy each other, have a lot of good things going. Please subscribe. And I actually lost a few subscribers due to the hacking of the site. So if you could come back and subscribe. If you discover that you're watching a video of mine and you thought you were subscribed and you're not, please resubscribe. Also, please like, and if you'd like to help support this channel financially, which I would greatly appreciate, go to dcastler.com/support and find a way that works for you. Until we next meet, 73.